Good morning, everyone. Let's start. So today we'll explore channel coding in some detail. But before I get into this particular topic, are there any questions from the previous class? Any questions? Okay. So just to recap, so we explored source coding or data compression in some detail in the previous classes. And we saw that no matter whether we looked at variable length compression with zero error or fixed length compression with vanishingly small probability of error, we saw that asymptotically, if you look at very large file sizes, raw file sizes, then the rate of compression, the optimal rate of compression turns out to be the entropy. Now, I'd like to clarify something. What we showed is that there exist compressors for which the asymptotic rate is close to the entropy, right? So you can achieve a rate of whatever entropy plus some epsilon for an arbitrarily small epsilon. However, we haven't shown that this is the best that can possibly be done. And that is something we will see towards the end of this course. We'll need to build some more mathematical tools in order to show that no matter what compressor you choose, the rate of compression must always be greater than or equal to the entropy. Right? So that's always good to keep in mind. Okay, so now we'll look at a different problem, and that is communication over noisy media. And just like for the data compression problem, we saw that the entropy turns out to be a natural quantity that appears as the minimum rate of compression. When we explore channel coding, we'll see another such quantity, which depends on joint distributions, which we call the mutual information. And this is another natural information theoretic quantity, which of course it is an operational quantity, but at the same time it also has an intuitive meaning, just like the entropy represented the amount of information contained in a particular random experiment. Okay, so in the previous class, we just looked at this block diagram of a generic digital communication system. So in any generic communication system, you typically have a continuous time signal, which is then sampled and converted to digital, which is then compressed and processed before transmitting through the noisy medium. And then at the receiver, you have a similar set of blocks where you sort of post process the received signal after demodulation, and then decompress and then reconstruct and convert from digital to analog. Right? So now the question is, assume that we have a sequence of information bits which is obtained after compression. How do we transmit this over a noisy medium such that at the receiver we can still recover it with a certain guarantee? Okay, and the way we will model this problem is in the following manner. So note that so the kind of pre-processing that is done is such that we are converting we'll assume that the continuous time signal is already converted to a discrete time signal, and so it is sampled and then maybe quantized. So it's converted from analog to digital and then compressed. Okay, so for us, the input to our system is going to be a sequence of symbols, right? So for example, if this were a speech signal, maybe this is a sampled speech signal. So you have n samples of the signal, and that is what you want to communicate to the receiver, right? On the other hand, if this were a problem of say transmitting some data over the internet, then maybe the input the input could be a sequence of bytes just coming from some higher layer application, and this needs to be communicated through the digital medium. Maybe you're searching something on YouTube, and your search query needs to be sent to the YouTube server so that they can send back the video to you. So you can view all of these as sequences of bytes. The goal is to send whatever n bytes through a noisy communication medium, which is maybe the wireless channel or a wired channel. Okay, so whatever it is, we will completely abstract out what we have. So the goal is to send whatever k, so a number of symbols through a noisy medium. And how do we actually model the medium itself? So we'll model the medium as a black box which acts as a random process. So if we give n symbols to the channel as input, then the output will be another sequence of n symbols. Okay, this is the model that we will stick to in this particular course. So n symbols as input, n symbols as output. Each symbol at the input comes from some alphabet. Let's call it calligraphic X, and the receiver gets a sequence of n symbols which comes from some other alphabet. Let's call it calligraphic Y. So we'll see some examples of channels, but this could be any particular input alphabet. So for example, if you're using in this particular picture, suppose that you're transmitting say QAM symbols, then maybe each xi could be a QAM symbol, it could be a QPSK symbol, or you could also model it as a sequence of bits. And similarly at the receiver, it could either be a sequence of bits or a sequence of real numbers. So for example, for certain kinds of channels, this could be the sequence of real numbers and so on. But whatever it is, that doesn't matter. It ultimately depends on how you model this particular channel. But for our purposes, the relationship between the input and the output is completely characterized by the channel law, which is basically a conditional distribution Pyn given Xn. Okay, so for us, the channel is completely specified by this calligraphic X, calligraphic Y, and Py given X. Okay, so basically we need three parameters to specify the channel. So the channel is specified by calligraphic X, calligraphic Y, and Pyn given Xn. So Pyn given Xn is called the channel law. Calligraphic X is called the input alphabet. And calligraphic Y is called the output alphabet. All right. So our assumptions, as I mentioned, are that time is this. We have discrete time signals, and we will assume that this channel law is known. So maybe it has been estimated beforehand, and that is what is typically done in most communication systems. You first estimate the channel. So we'll assume that this has already been estimated, and we'll make another assumption in this particular course. So we will assume that the way the channel acts on the input symbols is kind of independent across time. So each xi is corrupted to give a particular yi, and each xi is in some sense corrupted independently of the other xj's. All right. So the input to the channel is x1, x2, x3, and so on up to xn. Right, and the output, so for each xi, the receiver gets y1, y2, y3 up to yn. So somehow this vector of length n is corrupted to get another vector of length n, and the assumption that we will make is that each xi is independently corrupted of the other xj's. Okay, so this y3 conditioned on x3, it does not depend on the other xj's. Yes, is that right?
So what is the meaning of this corrupted? So like you mentioned, X is corrupted to.
I'll make that a little more clear. Uh, but basically what I mentioned is that how do you get the yn from the xn? So suppose that you give some xn as the input to this channel. All right. As I mentioned, the output yn is a random variable. It's a random vector, and so you'll see a particular yn with some probability, right? So given a particular xn as input, you'll see a particular yn as output with some particular probability, and that is specified by pyn given xn. And the assumption that we will make is that this joint distribution, this conditional distribution of yn given xn is IID conditioned on xn. So it has this particular form. So it is py given x of y1 given x1 times py given x of y2 given x2 and so on times py given x of y sub n given x sub n. Okay, or notationally this is the product I going from 1 to n py given x of yi given xi. So this is exactly what I mean when I say that each xi is corrupted independently to get a particular yi. So if you look at this distribution of yn given xn, so in some sense x1 is corrupted to get y1 and x2 is identically but independently corrupted. Uh, so x2 is independently corrupted to get y2 and so on. Okay, we'll see some examples which will hopefully clarify this particular point. But one other notation or one other terminology that I want to introduce is the n. So we're assuming that the input to the channel is a sequence of length n, and the output is also a sequence of length n. So this n is what we call the number of channel uses.
Sir,
Yes,
you said XIs are independently corrupted. So
yes,
this is like after passing over the channel. But just for
correct,
clarity, when we use this modulation scheme like this DPSK kind of
correct.
thing, there we tend to XOR. It's like two consecutive bits in, I think, in the demodulation part or something. Uh,
So that is why the way you model the channel is important. Uh, so if you view each quam symbol as one particular symbol, as a complex symbol, then uh, can you maybe mute yourself? I think there's a lot of echo.
Sorry.
Yeah, thanks. Yeah. So for example, if you look at say a QPSK symbol, now you can view this as two symbols, right? The real part and the complex part. But and then this is corrupted by whatever Gaussian noise, or maybe it is scaled and then corrupted. So if you view this as two different symbols, then there is some correlation. The corruption is not in some sense independent. But then if you view this as a single symbol, as a single quam symbol or a QPSK symbol, which is maybe scaled by a complex number uh, and then corrupted by additive white Gaussian noise, then each symbol is sort of independent of the other. So I'll come to these examples one after the other. We'll see a number of examples. And really the way you model ultimately, so our goal is to somehow, now all channels do not satisfy this particular property, this particular property, but as much as possible we will try to somehow set up by sometimes by carefully choosing y and x, we will try to make sure that it looks like that it has this particular form, that it is a discrete memoryless channel. Okay, I'll come to that point in maybe a couple of minutes. Okay, so as I was saying, so n, this term n is basically the number of channel uses, but it is also called the block length. Alright, so whenever I say block length or number of channel uses, they all refer to this quantity n. So calligraphic X is the input alphabet, calligraphic Y is the output alphabet, and for Pyn given Xn is the channel log. But we will assume that, at least for most part, we will assume that it has this memoryless nature. So Py given X is what we will call the channel log of the discrete memoryless channel, or sometimes called the transition probability. Okay, so all of these terms refer to the same quantity, and that is Py given X. Okay, so let's see some examples. So the simplest sort of example is the following. So you give a sequence of n bits as input to the channel. At the output, you see a sequence of n bits, and maybe each bit is flipped. So I transmit some sequence of bits, okay, and at the output I see another sequence of bits, y1, y2, y3, y4, and so on. And how do I obtain all the yi's? So this is x1, x2, x3, x4, x5, x6, x7. So each bit with probability p, it is flipped. So 0 becomes a 1 and a 1 becomes 0. And with probability 1 minus p, it is kept as it is. So basically you do the following. For each bit, each of these input bits, you toss a coin, a biased coin. If it is a head, then you flip it, you convert a 0 to a 1. If it is a tail, then you leave it as it is. All right, so maybe this is the this is the input sequence and this is the output sequence. Okay, so this is one example. So each symbol each bit is flipped, so 0 becomes 1 or 1 becomes 0 with probability p, and it remains as it is with probability 1 minus p, right? So if I give a long enough sequence, right, then what we can expect is that since each bit is kind of flipped with probability p, roughly p of the bits are going to be flipped, and roughly 1 minus p of the bits are going to remain the same as in the input sequence. Okay, so this is sort of the simplest channel. It is also called the binary symmetric channel, sometimes abbreviated as BSC, and it is specified by this parameter, the crossover probability, which is p. Okay, any questions?
So what you've written at the bottom is what, sir? That series of bits?
This.
Huh.
So just assume that this is the input sequence.
Okay.
All right. So the output sequence. If you look at the output sequence, then you get another sequence of bits. right? And in the output sequence, roughly p of the bits are going to be the complement of what it is in the input sequence, and roughly 1 minus p of the 1 minus p fraction of the bits are going to be the same as in the input sequence. Any questions? Okay, so in this case, let us try to see. Uh, so here, what is the input alphabet? It is just 0, comma 1. What is the output alphabet? It is 0, comma 1. And what are the conditional probabilities? So py given x, so of the probability of seeing a 0 at the output, given that 0 was transmitted at the input, so this is 1 minus p, and this is the same as py given x of 1 given 1 and py given x. So the probability that it is flipped is p given x of 0 given 1. Right? So this completely specifies the channel. So now let's try to analyze what happens when I give a sequence of a sequence of bits as input. Suppose I give xn as input given xn. Let's say that I had to calculate the probability of seeing a particular sequence yn at the output, given that I gave a particular sequence of xn at the input. So what would this look like? Is it possible to somehow get an expression for this in terms of p, n, and maybe something else? So it of course depends on the xn and yn, but what does it depend on? So uh, let me introduce some additional notation. So my goal is to calculate the probability that yn is the output of the channel, given that xn is the input to the channel. Okay, and I want to get an expression for this in terms of n, p, and maybe something else, but sort of the most compact expression I can get. So what I'll do is I'll introduce this new quantity. So given any two sequences xn and yn, both of length n, I'll define dh of xn comma yn, which is called the Hamming distance. So the Hamming distance between xn and yn is basically just the number of locations in which xn and yn differ. Okay, so for example, if xn is, let's say, 0 1 0 1 0 and yn is 1 1 0 1 1, then what is the Hamming distance between these two? Two, right? Because these two sequences differ in exactly two locations. The first location and the last location. All the others are basically the same. So this is 2, right? So similarly, the Hamming distance between 0 1 1 0 1 1, and let's say 1 0 0 1 0 0. What is this equal to?
6.
6. All right, because all, so they differ in all the locations. The first location is different, second location is different, and so on. So it's exactly the complement of the first. The second is the complement of the first. So the Hamming distance between these two is 6. Okay. So is it possible to find out what the probability? So assume that you're transmitting xn through a BSC, a binary symmetric channel with crossover probability p. What is the probability of seeing a particular yn at the output? So remember that each bit is flipped with probability p. It remains the same with probability 1 minus p. So maybe to take a very simple example, given xn. So suppose that I transmit 0 1 1 as input. So input to the channel is 0 1 1. What is the probability of seeing 1 0 1 at the output?
Probability of getting flipped per bit is p.
Correct.
So p square.
Mhm.
P square into 1 minus P. P square 1 minus P.
Correct. So it is p square into 1 minus p. So the probability that this gets flipped is p, this gets flipped is p, that this remains the same is 1 minus p. So it is p into 1 minus p. So it is p square into 1 minus p. Okay. So similarly, pyn given xn of which one? So let's take this particular example: 0 1 0 1 0 given 1 1 0 1 1. What is this?
P square into 1 minus p q whole cube.
Correct. So p square into 1 minus p the whole cube. And that is because, well, 2 of the bits are flipped and 3 of the bits remain as it is. Right? So now can we generalize for a give us for any xn and yn? What is p of yn given xn going to be?
So P to the power K 1 minus P n minus K.
Okay, what is k?
K is like number of
Lec
flips.
distance.
Correct.
Yes.
So k is basically the number of bits which are flipped, or in other words, for a given x and y n, it is a Hamming distance between the two, right? Because the Hamming distance is basically the number of locations in which they're different, or basically the number of bits of one that you need to flip in order to get the other. Right? So it is p to the Hamming distance times 1 minus p to the, well, dh number of locations have to be flipped, and n minus dh number of locations remain the same. Right? So for any x and yn, the probability that you see yn at the output, given that you had transmitted xn, is exactly this particular quantity. Okay. So that is good. Let's keep this in mind. So we'll use this when we do some more calculations later on. Okay. So this is the binary symmetric channel. It's a simple channel. Now let's see another simple channel which I call the binary erasure channel with erasure probability P. Okay, the binary symmetric channel, or the BSC, that was kind of, it's a natural kind of a channel, right? So you transmit bits, you receive a sequence of bits, and some of those bits could be in error. The error probability is P, and somehow the errors are independent of each other. So that's a natural model that one can think of. So here is another simple model, and it is the case when you transmit a sequence of bits 0, 1, 1, 0, 1, 0, 1. So you can imagine that there's someone sitting in between, who does the following. So given each bit is transmitted one after the other through this channel, and or maybe someone writes this down on a piece of paper, and there is a malicious person, or the way the channel acts is that with a certain probability P, this is erased or maybe just scratched out. So you scratch it out. Okay. So basically, you know that there is something over here, but you can't say whether it is 0 or 1. Right? So you transmit a sequence of n bits. At the output, you don't see n bits. You see some bits, and some of them are these scratches, or these locations are erased. Okay, and we call these symbols an erasure. Okay, so this is that was the input was a sequence of bits. The output is a sequence of symbols 0, 1, and E. So E represents that this particular location is erased, and the bit is left as it is otherwise. Okay, so some locations are erased, some locations are clean. Nothing has been done to it. Okay. So note that here a 0 never becomes a 1, a 1 can never become a 0. Either a 0 or a 1, they could be erased. Okay? And the probability that each symbol is erased is P. Okay.
Sir, erased in the sense how, sorry? What do we mean by erased?
So try to think of it in the literal sense, that let's say that you write down on a piece of paper. Okay, you write down, and then some locations are just erased out. Right? You know that there was something written in that particular location, but because it was erased, you don't know what it was. Okay, so for example, if someone writes whatever binary erasure, and maybe someone erases these particular locations out, you know that there is a space over here, which means that something was erased, but you don't know what the character was. Of course, in this case, maybe you can predict, uh, but but then there is a blank space over here, and this blank space is what I denote using this particular symbol E. Does that make sense? So think of it anyway. You can think of it as being erased, or maybe someone just smudges it, right, as I did over here. But basically, all this means is that once it has been smudged out, or once it has been erased, there is no way of determining whether at that particular location, if you don't see anything else, if you only see this particular location, it has been completely smudged out or completely erased. So you have no way of determining whether this at this particular location it was originally a 0 or a 1. Okay. Or if you want to think about it more abstractly, then this is exactly the same. So you transmit a sequence of bits. At the receiver, you see either 0 or 1 or E, where I call E the erasure symbol. And the probability, so the input alphabet is 0 comma 1, the output alphabet is now 0 comma 1 comma e. There are three symbols in the output alphabet. And what about the transition probabilities? So so the probability that you see a 0 given that a 0 was sent is 1 minus p, and the same the probability y given x of 1 given 1. The probability that you see an erasure at the output given that 0 was sent at the input is p, and the probability that you see an erasure at the output given that a 1 was transmitted, this is also equal to p. But the probability that a 1 is seen at the output given that 0 was transmitted at the input is equal to 0, and this is the same as the probability that 0 is seen at the output given that 1 was transmitted at the input. Okay. So let's again look at some examples. So let us suppose that I don't know, some sequence 0 1 1 0. Suppose that this is the input to the channel. So I transmit 0 and then 1 and then 1 and then 0. At the receiver, what is the probability that I will see E010?
Zero.
Exactly, very good. So this is 0 because at the input you had 0 1 1 0, and we're asking what is the probability that at the output 0 becomes E, 1 becomes 0, 1 remains as it is, and 0 remains as it is. So 1 can never become a 0. So the probability that you will see this at the output, given that this was sent at the input, is equal to 0. Any questions?
Sir, so
Yes.
practically in the output when we are receiving a sequence of bits, we either see 1 or 0. So this erasure means how do we get it in the
So,
output?
so one way to think about it is, can you mute yourself? Yeah, thanks. Yeah. So, of course, so this was originally introduced as a toy model, but one way to think about it is sort of packet drops in networks. So when you transmit a particular packet, which is not one bit but maybe a sequence of bits, when you transmit a particular packet from say from one source to a destination through some complicated network, then since you're using some kind of a routing protocol, some of these packets may reach exactly at the destination, but in between some packets may be dropped. So the sender sends a bunch of packets. The receiver could get these packets through the network, but some of these packets could be dropped. Okay, and you can think of an erasure as a packet drop. That's one way to think about it. Is basically a packet. Of course, so we're modeling this in the bit level here when we're talking about the binary erasure channel, but whereas really in practice it is not one bit which gets dropped but an entire packet. But again, these things can be generalized fairly easily. But right now we're focusing on a very simplistic kind of a channel because we want something that we can sort of do simple calculations with. Does that answer your question?
Yes, sir. Thank you.
Okay. Okay, so right now we were calculating these transition probabilities. So what is Pyn given Xn of, I don't know, so let's say that the input is again 0, 1, 1, 0, and the output is 0, E, 1, E. What is this equal to?
P square 1 minus P square.
Yes. Right, so there are exactly two of the symbols are erased and two of the symbols are left as it is. So P square times 1 minus P the whole square. Okay, so for general Xn, Yn, what do you think it will be? So assume that there are between Xn comma Yn, let me say eta of Yn comma Xn. So this is the number of erasures.
P to the power neta.
Okay, P to the eta. Is this it?
So like
What about the remaining location? So eta locations are erased and n minus eta locations are left as it is, right?
there'll be 1 minus P.
Correct. So it is P to the eta 1 minus P raised to n minus eta.
Provided
Yes.
we don't have this probability 1 given 0 and 0 given 1.
Correct. So assuming that Xn and Yn agree on the unerased locations, so a 1 never becomes a 0 and a 0 never becomes a 1. And if they don't agree on the unerased locations, then it is 0.
Sir, we can say in the unerased locations, the Hamming distance is
Sure. It's equal to 0. Any questions? Okay. So now let's see. So these are sort of simple channels, and these channels are again typically used in practice. But probably what is more commonly seen in most wireless or wired communication systems is what is called this additive white Gaussian noise channel, wherein now the inputs and outputs are not bits or they're not discrete symbols, but then they could be, say, real numbers, right, which is more common in practice. Or at least the output is going to be a continuous random variable, in most cases. So what is the model? So you transmit a sequence of, again, remember it's a discrete time system. So you transmit a sequence of numbers or a sequence of symbols, and each symbol is independently corrupted by Gaussian noise. So basically, for every time I send an xi through the channel, a single number through the channel, the output is going to be a real number, and yi is equal to x plus zi, where zi is a Gaussian random variable with zero mean and some variance sigma square, where sigma square is sometimes called the noise power, the noise variance, or sometimes the noise power. Okay, so this is exactly the model. Now it depends on what constraints you put at the input. So typically we introduce some kind of a constraint at the input. So one possible constraint, sometimes if you use a particular modulation scheme, right? So maybe if you are using something like BPSK, then maybe each xi is whatever plus square root p or minus square root p. Okay, so the input can take one of two values, either plus square root p or minus square root p, and the output is yi, and where yi is equal to, let me just move this out of the way. So yi, each yi is xi plus zi, where all the zi's are independent, identically distributed, and zi IID Gaussian with mean 0 and variance sigma square. Okay. Now maybe you want to use a different modulation scheme. Let's assume that you use QPSK or some QAM. Right. So one way to model it is that each xi comes from QAM, or maybe in general this could be some PAM or QPSK, QAM, any constellation, doesn't matter what the constellation is. So each symbol comes from that particular constellation. Right. So for example, it could be whatever, some 1 plus root 2j, 1 minus root 2j, minus 1 plus root 2j, and minus 1 minus, again this is just an example, minus 1 minus root 2j. So this could be maybe one constellation, whatever constellation it is. So xi can take one of these four values. So it is one of these four complex numbers. And now each yi is xi plus zi, but now zi is not a real number. It's not real Gaussian noise. It's complex Gaussian noise. It's complex Gaussian with mean 0 and variance sigma square. So basically you can write this as zi real plus j times zi imaginary, where each zi real and zi imaginary are both IID Gaussian, real Gaussian random variables. Zi real and zi imaginary are IID Gaussian, both with mean 0 and variance sigma square over 2. Okay, so this is an example of what is called a constellation constrained AWGN channel. So it's a constellation constrained AWGN channel. All right, and but sometimes, so this is what is commonly studied, but sometimes it's what is also studied, what is perhaps more commonly studied, is the power constrained AWGN channel, which is the following. So xn is allowed to be any set of real numbers, right? So each xi is allowed to be any real number, but you impose the following power constraint, that 1 over n times I equal to 1 to n, xi square should be less than or equal to p. So this is the power constraint. Okay, so, and of course yi is equal to xi plus zi, and where each zi is IID Gaussian with mean 0 and variance sigma square. Okay, so in this case, the input alphabet is R, the output alphabet is also R, and now the transition probability, it's not, you can't specify it by a transition probability mass function. So instead you specify using the conditional density function f of y given x of y given x. So of course this is Gaussian, 1 over square root 2 pi sigma square e to the minus y minus x the whole square by 2 sigma square. Right? But then now you have this additional input constraint that that this 1 over n times summation xi square should be less than or equal to p. So this is an example of an input constrained channel. All right. Any questions? Okay. So another example is the so-called fading channel, which is commonly seen in wireless communications. So now in wireless communication, you not only have noise being added to the transmission, but then there is also attenuation, and not just any kind of simple attenuation, you also have random fading. So one model is the so-called, so you can have this, what I call the fast fading channel. So yi is equal to hixi plus zi, where zi is Gaussian sigma square and hi follows some particular distribution This is also IID according to some density FH. Okay, so this is the fading distribution. Sometimes this is assumed to be Gaussian, sometimes it is assumed to be whatever Ricean, and so on. For different kinds of distributions, you get different fading channels. Okay, so this is the real fading channel. In wireless communication, sometimes you typically study yi equal to hi xi plus zi, where of course now each of these are not real numbers. So in this case, in the first case, both the input and the output is the set of reals, but now these are complex numbers, is the set of complex numbers. So Zi is IID complex Gaussian with mean 0 and variance sigma square, and each HI is again assumed to be IID according to some, it's again a complex number with some particular density. All right. So note the, again coming back to the earlier question which was there. So if you try to model this as, so here, let's assume that each Zi is IID complex Gaussian and each Hi is IID according to some complex distribution, some distribution on the complex numbers. If you try to split this apart, if you try to view this, you can view this as a sequence of n complex numbers or also as a sequence of 2n real numbers, right? So yn is n is a sequence of n complex numbers, or equivalently you can also view this as a sequence of two n real numbers. That's one way to view it. But now the difference is that Pyn given xn, so this corresponds to a discrete memoryless channel. But then if you look at whatever py tilde to n given x tilde to n, if you try to view this as a sequence of 2n real numbers, then this is not a discrete memoryless channel. It has memory because the real and the imaginary components are now dependent. They're not independent of each other. Okay, so that is why modeling the problem is extremely important. Okay. So one last thing before we end this class. So this can be extended to different kinds of fading models. The sort of more general fading channel is that each yi could depend not only on what is transmitted at the current time instant, but also on what is transmitted at the previous and the time instants before that. So here's an example of a simple channel. It's a frequency which is called frequency selective fading channel. So at a time instant I, so yi is equal to h0 xi plus h1 xi minus 1 plus h2 xi minus 2 plus zi, where zi is some IID noise. So this is not a discrete memoryless channel. This has memory. All right. So really we will not be looking at channels of this form in this particular course, but as it turns out, you can play tricks. You can also derive the capacities of such channels as long as under some conditions, as long as you know how to handle these. If each of the HIs are IID, then this is a discrete memoryless channel. But if these are not IID, if the HIs are not IID, if the ZIs are not IID, or if it's a frequency selective fading channel, then this is not a discrete memoryless channel. But then it turns out that you can do some transformations, you can do some approximations, and whatever theory you develop for DMCs can be extended to simple channels with memory. All right. So we'll stop at this point. Any questions? Any questions? Okay, so if not, then we continue in the next class. So see you all there.